Hello guys, and welcome to another calculus video. In this video we're going to be solving this awesome integral that you can see right here. It's the integral from 0 to infinity of square root pi over square root x squared plus 1 minus e to the x squared over 8 times k naught. Now this k naught is a type of Bessel function which we'll go over in a moment. K naught of e to the x squared over 8 over 2 dx. And so this was suggested by a viewer of mine, Almonius, and it's a pretty fun problem, so we're going to go ahead and solve it right here. So k naught is the modified Bessel function of the second kind of order 0, and it's defined by this limit. The limit is a goes to 0 of pi over 2 of I negative a of x minus I a of x over sine a pi. Now I n of x is the modified Bessel function of the first kind, and so the modified Bessel function of the second kind is derived from this function. And there's a few different representations of this. We have the integral from 0 to infinity of e to the negative x hyperbolic cosine of t dt, or the integral from negative infinity to infinity of e to the negative I xt over root 1 plus t squared dt. Whenever I deal with bizarre special functions like k naught in this integral, I like to have a few different series or integral representations on hand that I can try and apply to see which ones are going to help me to actually solve the problem. So with this problem, I actually was trying to use this second definition down here because it really matches up a lot better with our integral, but it actually turns out that this first definition is a little bit better for solving this integral, at least through the method that I used to solve it. So the first thing we're going to do is just go ahead and directly substitute in that definition of the modified Bessel function of the second kind. So we get this integral right here. And notice that we can't do any shenanigans with swapping the order of integration because we have this other term over here that actually you can't switch the order of integration because this doesn't have anything with t in it. And so you'll see that we're actually going to switch the order of integration later, but first we're going to need to do a lot of simplifications on this first integral. So the first thing we're going to do is bring this e to the x squared over 8 on the inside, and then we get 1 minus hyperbolic cosine of t. Now, this might remind you of something with cosine, and that's that 1 minus cosine of t is related to sine squared of t over 2. And so we're actually doing the same, basically the same identity here. If you take hyperbolic sine of t and you square it, you get e to the 2t minus 2 over 4 plus e to the negative 2t also over 4. And this is the same as 1 half cosh of 2t minus 1. So if we replace t with t over 2, we'll actually get this expression right here, just negative. And so that means we can substitute in here e to the negative x squared over 4 times hyperbolic sine squared of t over 2, and a negative sign in front here. Then to get rid of this t over 2, we'll just get u equals t over 2, and that also gets rid of the 1 half in front here. So we get sine h squared of u on top right here. Now notice that we're actually sort of missing something that still has to do with this integral because, again, we want to combine both of these integrals into one big integral and then be able to interchange the order of integration. However, we want to get them looking kind of similar. We want them to be very similar in general because that'll actually help us in solving the integral because that will make the two functions work together more nicely. So what I tried to do here to get this right side to look more like the left side with the square root x squared minus x squared plus 1 is I let v equals sine h of u. And the reason for that is that means that sine h inverse of v is going to be u, which means that du is going to be 1 over root v squared plus 1 dv. And that gives us this right here. We now have square root x squared plus 1 and square root v squared plus 1. But we still want one more step to make these two look very, very similar because, again, this is root v squared plus 1, this is root x squared plus 1. These are completely different variables. So if we want to get an x squared inside here, what we can actually do is let v equal y over x. This means that dv equals dy over x. And first of all, this simplifies this exponential greatly because this just becomes e to the negative y squared over 4. And then we put y over x squared inside this square root. And then this x from dy over x is going to be multiplied into the square root, and we'll actually get this right here. Integral from 0 to infinity of square root pi over square root x squared plus 1 minus the integral from 0 to infinity of e to the negative y squared over 4 over x squared plus y squared dy dx. Now we're looking a lot better. Everything looks very, very, very similar. There's just a few things that we still need to deal with. First of all, we need to get this first integral somewhat in terms of y, and specifically what we want to do is we want to rewrite this as an integral from 0 to infinity with respect to y, because then both of these terms will be integrated from 0 to infinity with respect to y. We can rewrite them as one integral, because the integral of f of x dx plus the integral of g of x dx is the same as the integral of f of x plus g of x dx. So in this case, we want it to look very similar to this function right here, and it actually turns out, if we look at e to the negative y squared over 4, and we integrate it from 0 to infinity after u equals y over 2, we find that this is actually equal to square root pi. So that means we can replace this square root pi right here with the integral from 0 to infinity of e to the negative y squared over 4 dy, and then we can combine these two integrals into one double integral right here. So that's what this looks like. We have the integral from 0 to infinity of the integral from 0 to infinity of e to the negative y squared over 4 over square root x squared plus 1 minus e to the negative y squared over 4 over square root x squared plus y squared dy dx. Now, this is a very difficult flip to do, and I'm not going to go through all the math required to actually show that we can interchange these integrals, but we can actually use Fubini's theorem here. It's just very, very nasty to apply. Sorry, I kind of misspelled that there. But essentially, what we're going to interchange these the integrals, and then we're going to factor out e to the negative y squared over 4, because this is a constant when we're integrating with respect to x. So we'll get integral from 0 to infinity of 1 over square root x squared plus 1 minus 1 over square root x squared plus y squared dx dy. And we're going to use the formula integral of 1 over square root x squared plus b squared dx equals inverse hyperbolic sine of x over b plus c, which is the same as natural log of x over b plus square root of 1 plus x over b squared plus c. So, when we integrate these two terms using those formulas, we get this right here. And at 0, this is simply going to disappear because inverse hyperbolic sine of 0 is just 0. However, at infinity, we have these two natural logarithms that are going to be subtracting each other, and we can rewrite this as a ratio here. Natural log of x plus square root x squared plus 1 over x over y plus square root x over y squared plus 1. Now, in this case, notice that on the top here, it's essentially the same thing as the bottom. We're just multiplying by 1 over y on the bottom. So the ratio of the top to the bottom as x goes to infinity is just 1 over y, or just natural log of y overall inside that natural logarithm. You can also prove this by dividing by x on the top and bottom in here, but I just went ahead and said that the ratio of the coefficients here is going to be 1 over y. So we get integral from 0 to infinity of e to the y squared over 4 times natural log of y dy. Now, letting y squared over 4 equal alpha, we get that 2 root alpha equals y, or dy equals 1 over root alpha d alpha. And that gives us this integral right here, the integral from 0 to infinity of natural log of 2 plus 1 half natural log of alpha times alpha to the negative 1 half times e to the negative alpha d alpha. And now we're going to get this all in terms of the gamma function. So separating out this first term, we get natural log of 2 times integral from 0 to infinity of alpha to the negative 1 half times e to the negative alpha d alpha. Now, this right here is simply gamma of 1 half, so we're going to get natural log of 2 times gamma of 1 half. Over here, we're going to get 1 half integral from 0 to infinity of alpha to the negative 1 half, natural log of alpha e to the negative alpha d alpha. Now, this natural log of alpha makes it a little bit more difficult to deal with, but no worries. All we have to do is take the definition of the gamma function and take the derivative with respect to x, or in this case with respect to alpha, I suppose. Or not, it wouldn't be alpha, with respect to x, with respect to this exponent here, and we find that this is actually going to be the derivative of the gamma function at x equals 1 half. Now, in order to actually calculate gamma of 1 half, we're going to use the digamma function. Digamma of 1 half equals gamma prime of 1 half over gamma of 1 half, and digamma of 1 half equals negative gamma minus 2 ln 2. I have a video on how to calculate that if you wish to see it. I'll link it as a card right here. This means that gamma prime of 1 half is digamma of 1 half times gamma of 1 half. Gamma of 1 half is just root pi, so we get root pi times negative gamma minus 2 ln 2. And again, substituting in gamma of 1 half equals root pi, we get root pi ln 2 plus 1 half root pi times negative gamma minus 2 ln 2. Notice that actually if we multiply all these terms out, that the 1 half times square root pi times negative 2 ln 2 just cancels with this square root ln 2. Or square root pi ln 2, so we can cancel out those terms, and all we're left with is our residual term, minus gamma square root pi all over 2. What an absolutely awesome integral. Thank you so much to Almonius for suggesting this integral, and thank you so much for watching the video. I hope you guys enjoyed, and thanks for watching. See you next time.